Good morning, everyone. So here's where we are in terms of what material we've covered. We actually are almost done here with 7.5. We need to just finish up one more thing. And I did the video for the homework, and I kind of covered it in the in the homework, but we're just going to wrap that up, and then we're going to start 7.6. We should finish 7.6 today, and that will be all of the material that will be on your exam. So all of this will be exam 1 material. Okay, and that exam will take place next Wednesday. All right. And
I have a question.
Yes.
Will we be covering only those until the exam, or will we move past those units?
No, next Monday we will do 7.7.
Okay.
But you won't be tested on it. That'll show up on the next test. Okay. All right. So let's get going here. Any questions? We're good. All right, so we're continuing 7.5. The last topic at the end of the section had to do with even and odd functions. And this is a topic that you cover in college algebra, but I'm just going to do a quick review of it. And then we'll talk about how that, how we correlate the even and odd to the sine and cosine and tangent. So back in college algebra, you were told that a function is said to be even. Okay, we call a function an even function if f of x equals f of negative x. And then we call it odd if f of negative x equals negative f of x. And I know, in my experience teaching college algebra, students seem to have some issues with this. I think there's a very easy way to see this geometrically. So I've given you an example of an even function and an odd function here. The first one is f of x equals x squared. Now, to understand why we would call this function even, what we could do is we could pick some x value. So like, for example, if I pick the number, let's say 1, okay, and I plug that into the function, of course, if we take 1 and we square it, we get 1. But notice that if we take -1 instead of +1 and plug that into the function, we also get 1. So we have the same output, right? These y values are the exact same answers, even though I'm plugging in different numbers. I'm plugging in 1 and then I'm plugging in its opposite, -1. And that's what this is saying. This is saying when you plug in some number, in this case I plugged in 1, you get the same thing as if you plug in -1. Okay, we have equality. Now that would work for any value of x I plug in. So if I pick another number, let's say I pick 2, I plug that into the function, square it, I'm going to get 4, but I get the exact same answer if I plug in -2. I also get 4. And so any function that has that property is called an even function. So an easy way to tell whether or not a function is even is to look at the graph, and if it is a reflection of itself over the y-axis, then it is even. So do y'all see that? If you were to imagine doing like an imaginary line right down the middle, that if I reflect this side over to that side, it would land right on top of itself. You'll see that? That's what makes it even. Now, odd is a little different. So let's look at f of x equals x cubed. This is an odd function. Now let's see why. So let me again pick a number. So if I pick the number, let's say 1, and plug it in, well, 1 cubed gives me 1, right? So 1 cubed would give me 1. But if I plug in -1 instead of +1, I don't get 1, do I? I get -1. So they aren't the same, right? When I plug in the +1 and the -1, I get 2 different answers, but they are similar to one another. They're the same answer, they're just opposite in sign. Let me do it again with a different number. Now, unfortunately, my graph doesn't go far enough here. Oh, you know what I'll do? I'll go to the graph over here. Hold on. was the one I just had? Oh, I think I got rid of it here. I'll just do it here. Okay, so here we go. There we go. Okay, so if we look at the graph here, come on. I can't quite fit it on. There we go. So here's x cubed. If I were to take the number 2 and plug it in, I'm going to get 8. If I plug in -2, I get -8. So again, you're not getting the same answer. When I plugged in 1, I got 1. When I plugged in -1, I didn't get 1, I got -1. When I plugged in 2, I got 8. And when I plugged in -2, I got -8. So basically what's happening is that the answers, these two things here are not equal, right? F of 2 is not equal to f of -2, but they're off by a sign, right? One of them, if one of them is positive, the other one will be negative. And so that's what the odd property is saying. And let me go back to this. It's saying that if we plug in some, let me do it this way. If we plug in some positive number, let's say 2, we know that in this case we got 8. If we make it negative, then it will match what we get when we plug in -2. So the difference here is that we have to put a negative in front of this instead of it just being f of x. So I hope that makes sense. Graphically, it's not a reflection. Do you see that if I reflect this over the y-axis, it doesn't land on top of itself? But it is a reflection in this sense. It's a double reflection. So imagine that I took this part of the graph here and I reflected it over the y-axis, it would land over here, right? But now imagine that I reflected along the x-axis, so I reflect it this way. Now it would come down and it would land on top of this. So it's like a reflection over the y and then followed by a reflection over the x. We call that a reflection over the origin. That's what it's called. I just look at it as a double reflection, okay? So even functions are reflections over the y-axis. Odd functions are reflection over the y and then follow that with a reflection over the x. Okay, so why are we talking about even and odd functions? Well, because the sine function, certain trig functions are even and certain ones are odd. So let's see, this is it, this tells you right here, but let's try and determine this on our own. So remember that when we're talking about the sine function, let's start with sine of theta. Okay, theta is the thing I'm plugging into the function, right? Theta right here is my input. And I'm gonna get an answer, right? When I plug in theta, I get some answer. And because we're talking about sine, it should be the y coordinate, shouldn't it? On the circle. So I'm gonna just pick some arbitrary value of theta. Here we go. I'm just gonna go right there. I'm gonna call that theta. And I'm gonna go out here to this point. And the y value would be this distance right here. That y value is exactly what sine of theta is. Do y'all agree? Whatever that height is the value of sine of theta. Now, what about if we plug in negative theta? So let's plug negative theta in instead. So let's rotate the other direction by the same amount, theta. And let's look at this angle. And let's look at this. That is sine of negative theta. Right? It's the y coordinate. Any questions on why that's sine theta and sine negative theta? Are y'all okay with that?
So if it's a negative theta, it's gonna just be a negative answer, correct?
Well, in this case, it is, yes. Sorry, I should have put a negative in front of that theta. In this particular problem, right, because of where theta lies, we have a negative answer. What I want you to think about is whatever this distance is right here, whatever that distance is, how is that related to this distance? Are they the same?
Yeah.
Well, if you measure them like with a measuring tape, they're the same. But because this one is in the first quadrant, wouldn't we get a positive number? And then because this is in the fourth quadrant, wouldn't we get a negative number? So these two values, even though if you measure them with a measuring tape, they're the same length. One of the answers is positive and the other one is negative, which means that if you take theta and plug it into sine, you do not get the same thing as you get when you plug in negative theta, right? These are not the same. One of them is positive and one of them is negative, right? So what I need to do to make this equal is I would have to change the sign of one of them. So like here, I just make that negative in front of this one. And now these would be the same because I've changed the sign of this one. Now that is exactly what it means to be odd, right? Go back up here. We said if you plug in some number and then change the sign, it's equal to what you get when you plug the negative of that number in. That's what I'm saying here. You plug in theta, figure out what sine is, change the sign. That should be equal to what I get when I plug in sine theta, negative theta. Does that make sense? I know it's a
Are all
little.
of these in the theorem box negative?
Pardon?
Are all of the ones in the, which ones? The cosine and the secant are positive, correct?
Yeah, so right now, all we have established is that the sine function is odd, okay? The sine function is an odd function. That's all we've established at this point.
All right.
Now, cosecant, okay, cosecant is the reciprocal of sine, isn't it? It's just 1 over it. So that doesn't change anything. It still is an odd function because all you're doing is flipping the fraction over. So cosecant should also be odd, all right? Now, what about cosine? So let's start over. Let's start over with cosine. And I want to keep this, so I'm going to just copy this and go to a different page. So let's talk about cosine. If I were to take cosine of some angle, let's see what happens. I pick some angle theta. I go here. Now, cosine is which coordinate, the x or the y?
X.
The x, right? So what we can imagine is that cosine of x is actually this distance from here to here. That would be the x coordinate. That's cosine of theta. Do you all agree with that? Instead of it being this side of the triangle, it's this like adjacent side instead, right? So that's what cosine of theta would be. It would be that length from here to here, which right now is a positive number, right? Because it's to the right of the y-axis. Now, what if I take negative theta? So I go this way, that's negative theta. And I come here and I draw my triangle. Now, again, it's the x coordinate. But isn't that exactly the same? Aren't those exactly the same? These two x coordinates are identical, right? It's not like the previous one where one of them was above, so it was positive, and the other one was below, so it was negative. We didn't have that they were off by a sign. Here, they're exactly the same number. And that would actually work no matter where you draw your theta, by the way. It would not have to be in the first quadrant. So like if you decided to pick your theta and say, let's let theta be there. Okay. Now your x coordinate is here. That's cosine theta. But if you take negative theta, which would go the other direction, like that, draw your triangle like this, you still have the same x coordinate. Okay, no matter whether you go this direction or this direction, you still get the same coordinate for the x value. The y values, of course, are going to be off. They're going to be different. They'll be off by a sign. So what that means is that for cosine, if you plug in theta, you get the same exact answer as if you plug in negative theta. And that's exactly what it means to be even, right? Even means when you plug in the negative, it's the same as plugging in the positive. So we have this property, I'm gonna do it in green, that cosine of theta, that is even. Now, what do you think about secant? It's just the reciprocal of cosine, right? So it should also be what?
Even.
Even. Okay. So the green is even, the yellow is odd. Now, tangent and cotangent are a little bit harder to show. So in an effort to save us a little bit of time, I'm just going to tell you what they are, and then we could verify it. We could draw pictures, but I'm not going to. For now, it's just important that you know that both of these are odd, okay? So out of all of the 6 trig functions, only 2 of them are even, cosine and secant. The rest are odd, okay? All right, so that's it. That's it for this section. We're ready to move on. Any final questions for this section, or can I proceed?
So, like this was what you did on the video for 7.5, where you said we didn't cover it. This is exactly how we did those problems.
Well, I had never talked to you about what even and odd were. I'd never discussed it, but then in the homework, you had to use the even and odd properties to solve some problems. Now I've established why it is the way it is, and then now you can use this. See, basically what this says is that, like, if you wanted to know what cosine of negative 45 degrees is, well, you don't even have to worry about the negative 45. You can just do 45. And then you can go to your unit circle, or go to your circle, go to 45 degrees. Cosine's the x coordinate, so you just look at that √2/2. And so your answer is √2/2. And the reason why you can just eliminate the negative and not worry about it is because cosine is even, right? Cosine is even, so that means you can just look at that. Similarly, if you wanted to know what sine of negative 45 was, well, since sine is odd, you could say, okay, forget the negative 45, I'm going to do sine of 45. But because it's odd, I have to put a negative in front of that answer. Okay, that's what this is saying right here. If I'm going to do sine of negative 45, I can do sine of 45 and then do the negative. So then again, I would go to the unit circle, I'd go to 45 degrees. I'd get the y coordinate this time. So sine of 45 degrees should be √2/2, but I have to make it negative. So this would be negative √2/2. Okay. Now, this does come into play later. The even and odd properties of sine and cosine come into play. As we move through this class, there will be times where we'll have a cosine function, it'll have a negative in it, and all of a sudden on the next line, we're going to get rid of the negative. So you don't want to be like, okay, well, where'd the negative go? Because it didn't go anywhere. We're just using the property of the even property of cosine to get rid of the negative. All right, so yeah, we'll see when we get there. All right, so we're going to start 7.6. This will be the last section that will be on the test. And this is a critical section, okay? Because the next few sections, how well you do in the next few sections are dependent upon your understanding of this section, all right? And we've put everything in place now to start to look at the 6 trig functions as functions and look at their graphs. So let's just back up a second and let's just remember what a function is, right? So a function simply takes in a number, right? You plug some number in, the function does something to that number, spits some number out, right? So you have an input and you have an output. Very basic example, f of x equals x squared. That's a college algebra parabola, right? We know that the input here was x, right? And you plug in 0, square it, you get 0. You plug in 1, square it, you get 1. You plug in 2, square it, you get 4. 3, square it, you get 9. -1, squared 1, right? -2, squared 4, right? So you have input, output, yeah? Well, what we do is we try and figure out if there's a way we can visualize this function. Okay, so is there a way that we can give some visual representation to what this function is doing? So what we do is we draw these two axes, right? Your X and your Y axes, right? Now that's what you've done. This is not new, but I want you to kind of look at it in a different way. When you look at your input, do you all agree that all of those numbers basically are numbers on a number line, right? So if I were to look at my inputs, I could say, here's a number line, right? Here's 0. And the inputs that I've put in here, 1, 2, 3, -1, -2. So what I did is I took these inputs, for example, let's do the 2, right? So I took 2, which is here, and that number, I sent it through the function, right? And when it got sent through the function, it got dropped off. Where did that number 2 get dropped off?
At 4. Positive 4.
Yeah, on another, on another number line, right? If this is 0, this number 2 gets sent over here to 4, doesn't it? So this would be a really crappy way of drawing what the function is doing, right? I would have to do this for each number. So if I did, let's say 1, right? If I want to know what happened to 1, 1 would get squared and come out and become 1 over here. But then that would be a problem, because if I did -1, then that would come over here, and then that would also go to 1, wouldn't it? And so do y'all see this is not a very good way of like visualizing what the function is doing? Like, it's okay, but it's not great. So what we do instead is we take the input axis right here. We take that number line and we draw it here, okay? And then we take the output axis and we rotate, we turn it vertically and we draw it here. And that's what a graph is. It's just those two, it's this visual, it's these two axes drawn together in one picture. So what we have now is that this is our input and this is our output, right? So if we want to say what happened to the number 2, well, where did the number 2 go? It went to the number 4, so I go up here to 4 and I represent it with a point, right? So you have your input is 2 and your output is 4. So it's like an ordered pair, 2, 4, point. And we can do that for all of these. If I plug in 1, it spits out 1. So I draw that point. And I do this for all the points, right? And that's where the picture comes from. The picture comes from that, all those dots together. Okay, any questions? Okay, what we want to do now is the exact same thing for the sine function and then the cosine function. Those are the only two we're going to talk about today. Next class, we'll talk about tangent, cotangent, secant, and all that stuff. But today, it's just the basic two trig functions, the most important ones, sine and cosine. So we want to look at sine and cosine as being functions. So let's start to try and get our heads around what this is going to be. So far, we've just been looking at sine theta, right? That's it, sine theta. What I'd like for you to do now is I'd like for you to kind of, I don't want you to throw this idea away. It's not throwing it away. What we're doing is we're going to try and define a function. But now the input is going to be x, not theta. Oh, I didn't write. So x is the input, all right? But I want you to understand that x is still an angle, all right? It's still an angle. And I want us to talk about what would happen if we started plugging in different values of x into this function. And then we're going to try and visualize it. So remember, x is an angle. Please don't forget that. X is an angle that we're plugging into the sine function. And let's just start with the angles that we know. All right, so it's time to put people on the spot. Okay, is Isa here? Or S? Not Isa. Esa.
Yes, I'm here. You said it right the first time.
I did?
Yeah.
Okay, good. All right. Give me one of the common angles and give me the sine of that angle.
Like the one that's like the pi over 3, like one of
Yeah,
those.
whatever. Yes. Why don't you start here? I'll start us out. How about at 0? I'll start us at 0.
Okay,
So
hold
at
on.
0, and we're going to do everything in radians, by the way. We're not going to use degrees. Okay. I want all of our angles in radians. Okay. So at 0, what is, Isa, what is the sine of 0?
Isn't it just 0?
It is 0. Okay.
Okay.
Let's go to the next common angle, pi over 6. I'm going to keep you on the spot.
Okay.
Sine of pi over 6.
Isn't that 30?
That's 30 degrees. Yes.
Yeah.
What is sine of it though?
Hold on. I don't know. If I'm being completely honest.
Do you know where to go to find it?
In the little graph thing, but
Okay. So this is where we're looking at this 30 degrees. You're looking at the point. Do you know which of these coordinates you're looking at?
yeah, isn't it that the square root of 3 over 2 and then
And then 1/2.
yeah,
Okay, but which one is it? Is it this one or this one?
the first one.
It's the sine function. So sine will always be the y coordinate.
Okay.
Okay. All right. So look, I'm just going to be honest with everyone here. Okay. And this is not Isa. This is not, I'm not trying, I want all of y'all to succeed. Okay. I want all of y'all to do well. If you're not familiar with the fact that the sine is the y coordinate at this point, you have a long way to go before next Wednesday. All right. There's a lot that you have to get under, get in control, because we should all be at a point right now that if I ask you any of these common angles, I should be able to ask you sine or cosine of any of those, and it should take you less than 10 seconds. All right. It should take you like 3. All right. Now, if you have a picture of the circle, it's even better, but you should know where you're going, like what you need to do to get the answer. Okay. So don't take that as me taking a shot at anybody or you, Isa. It's just, I don't want to paint a picture that makes anyone in this class believe that they are further along than they are. You know what I'm saying? I'm just trying to be straight up with everyone. You need to be able to pull these answers quickly. So sine is sine of pi over 6 is 1/2. Okay. Let's move on. How about Leslie?
Yes.
Okay. Leslie, how about you get the next angle? Now I've got everyone scared. How about pi over 4? Sine of pi over 4.
Yeah. So the sine of pi over 4 is root of 2 over 2.
Root 2 over 2. Okay, good. How about pi over 3? That's 60 degrees.
So the sine would be root 3 over 2.
Root 3 over 2. Good. All right. We're going to keep going. You want to go one more? Sure. Okay, good. Pi over 2. Sine of pi over 2.
The sine would be 1.
1. Great. Okay, good. So that the way that Leslie responded there is the way that I would hope everyone could be in the next 24 hours. Okay, that you can do that. Now, Leslie, were you looking off the picture?
Yes.
Okay, so that's okay. All right, but you have to remember that on the test, I'm not providing you a picture, right? So everyone has to know this first quadrant. You've got to know that first quadrant. So what I would recommend on the test is that the first thing you do when you start the test is draw the first quadrant. Like just put it in your memory and then just draw the first quadrant as soon as you start the test if you don't have it memorized. And that way you have it for the rest of the test. That would be my recommendation. I'm not a big memorizer myself. I'm not real big on that, but there are certain things in math you just have to know, and this is just one of those things you need to know. Okay, let's keep going. I want to do more angles. Okay, Tyler, you around?
Yeah.
Okay, Tyler.
So then the next angle, it'll be 2 pi over 3. And then,
Okay, oh, you're saying what is the next
oh, sorry.
angle? Okay, yeah, you want to go 2 pi over 3?
Yeah.
Okay, so just so everyone knows, here's where we are. We've done 0. we've done pi over 6, we've done pi over 4, we've done pi over 3, we've done pi over 2, and now we're doing this one, which is 2 pi over 3. And what is that? The sign of that?
The sine is going to be square root of 3 over 2.
Root 3 over 2. And then how about, what's the next common angle?
It'll be 3 pi over 4.
3 pi over 4, and that gives you root 2 over 2, right? And we can keep on going, right? All right, good. You're done, Tyler. So let's now, this is where things are going to change, okay? This is the point. Right now, we are going to transition to something different right now. What we're going to do is we're going to try and visualize this. So we're going to draw the two axes. And I want you to understand what we're drawing here has nothing to do with the picture of the circle anymore. Okay, this is a brand new picture where the input is the x, which is the angle. Very important. The input is the angle, okay? And the output is sine of that angle, okay? So it's just all of these graphed. Okay, so 0, 0, that would be here. That's the point 0, 0. My next point is pi over 6. So if you were to get on your calculator and do pi over 6, you get about 0.52 something, but that doesn't matter. I'm gonna call this pi over 6. And what is the value of the sine function at pi over 6? Well,
Half.
a half, right? So I'm gonna go up, let's say that's 0.5. Let's say that's 0.5 right there. I'm going to go up to here. And then I'm going to go to pi over 4, which is here. And the value there is square root of 2 over 2. So let's figure out what square root of 2 over 2 is. I'm going to do that on my calculator. Square root of 2 divided by 2. I get 0.707. So let's say this is 1 up here. 0.707 would be, I don't know, I'm going to estimate this to be about right there. Y'all see that it's between 0.5 and 1, somewhere in here. And then I'm going to go to pi over 3, which would be here. And it's going to be root 3 over 2. So I do that on my calculator. I get about 0.86. I should put these here. 0.866. This was 0.707. This is 0.5. Of course, that's just 0. So 0.866 is pretty high up there. And then when I get to pi over 2, I finally get up all the way to 1. Now, just like with the parabola that I drew a second ago, we get these points, right? And then we connect them all together with this nice little curve. Well, that's what I have here. If I were to plug in other angles, I would get a nice curve like this. Is this making sense, everyone?
Yes.
Okay, now what we would need to do is continue, right? And just continue plugging in angles. So we could do that, but I have a better way of doing this. Okay, let me show this to you. All right, this is the exact same picture. Let's see if I can fit that all on there. All right, so here's the unit circle. Here's a separate picture of what the sine function looks like. So what we were doing is we were plugging in angles, right? We took 0, we plugged in 0, it spit out 0. So that's this point. Then we plugged in what, pi over 6? When we plugged in pi over 6, we got 0.5. So that's this point right here. And then we plugged in pi over 4, and we got about 0.7, and that's this point here. So do you all see, I don't know if it's going to let me do this. Do you all see that this point right here is basically this height, because sine is the y coordinate, right? Sine is the y coordinate. So what I want you to focus your attention on here is I'm going to animate this. I'm going to just press play here, and let me slow it down. Whoa, whoa. Hold on, I got a problem. Got a problem with my code. I gotta change something real quick. 2 pi. I'm gonna try that again. There we go. Okay, so what I want you to pay attention to here is that all we're doing is we're going around and we're plugging in different angle values, right? So the green is the input here. The green is the angle, and the red here is a measurement of the y coordinate. So all we're doing is we're taking that green angle, and instead of looking at the green angle as this angle going around a circle, the angle is actually our x-axis now. And then the output is just this red. So those dots, you see, they're just the same height, right? They're going up and down together. Does that make sense? Yeah. And so what we get when we look at this, what we get is what's called a sine curve. All right, this is a sine curve. And what's going to happen is we start at 0, we go up, we hit a peak at 1, and then we come back down, we go through 0 again, we come down to -1, then we go back to 0. And then what's going to happen if I were to keep going? Can someone tell me if I were to continue?
We're going to go back up to 1.
Yeah, it's going to repeat itself, isn't it?
Mm-hmm.
It's going to do the same thing. And what if I went and did negative angles? What do you think the picture would look like over here to the left?
It would drop down and then go back up. And then...
Yeah, it would just be a continuation of this curve. So what we're looking at here, this right here is called one period of sine. Okay, it's one period of sine because this picture right here is the rest of the graph is just going to be a bunch of copies of that picture. All right. And I have another thing we can look at for that. Oh. So here's the sine curve right here. All right, and you can see that as I go through here, start at 0, I go up. At pi over 2, I'm at 1. At pi, I'm back at 0. At 3 pi over 2, I'm at -1. And then I get to 2 pi and I'm back at 0. Once I get there, it's just another repeat of the same thing. Boom, there's another period. And then we go again, another period, right? And there's an infinite number of periods, okay? I'm zoomed out way real far, but it's an infinite number of periods and it goes in both directions forever. And that is your sine curve. All right, any questions on that sine curve? When you look at this sine curve, I think it's a little bit easier now for us to talk about domain and range. Because when you talk about domain, you're saying, okay, does the graph exist to the right and to the left forever? So can you go in both directions forever?
Yes.
Yes, so the domain would be everything, right? All real numbers. And the range are the outputs. Do you see that our outputs are stuck between -1 and 1? So the range, the only outputs that we ever get are between -1 and 1. Now we talked about domain and range before, and now you can maybe see a little bit better. Question?
We'd use brackets, right? Because it actually touches the point on the graph.
Yeah, I was going to write it down here. Domain of this would be everything. Okay, all real numbers. Actually, I should put the domain is any x value that's an element of the interval -infinity to infinity. That's the interval notation. Set builder would be something like all x such that x is bigger than -infinity, less than infinity, something like that. You could also say x is an element of the real numbers. That would work also. All three of these are okay. So domain, you can plug any number you want into the sine function. There's no restrictions. Now in terms of range, gosh, I can't write. Range, it's the outputs. And the outputs all have to be between -1 and 1. Now, can it ever be 1 and -1? Does sine ever actually spit out the number 1? Pi over 2, right? At pi over 2, sine of pi over 2 is 1. And sine of 3 pi over 2 at the bottom of the unit circle is -1. So the range would actually include -1 and 1. And so you would put -1 and 1 in brackets, not in parentheses. So hopefully now that we have a picture of sine, like a graph of it, it's easier for us to see domain and range. Hopefully. Any questions? All right, so what are the things you need to know? You need to know that the sine function starts, well, the basic sine function, f of x equals sine of x. You need to know that it starts at 0, 0, and the first period ends at 2 pi. You need to know that one period happens in 2 pi. You need to know that halfway in the middle of this is pi. And you need to know that this is pi over 2. And you need to know that this happens at 3 pi over 2. See, there's like 5 important points on this function that we're going to use as we move through this section. There's 5 important points. We have the starting point, the ending point, and the middle point, right? Notice that all of these 3 blue points are x-intercepts of the function, right? They're where the graph hits the x-axis. The other 2 important points are where we have a peak and a valley, the highest and lowest points. Those 5 points are going to be critical for us as we move through, because our ultimate goal is for us to be able, to provide you a sine function and for you to graph it. And so the way we're going to do it is by using 5 points. And you'll see when we get to it. So for right now, everyone needs to understand sine starts at 0, ends at 0. I'm talking about y values. Okay, that happens in a period of 2 pi. The middle value is pi. We have an x-intercept there. And then the peak here is at pi over 2, and the valley here is at 3 pi over 2. Okay, that's what we need to know going ahead now. Questions? I think it's time to look at cosine.
Sorry, the pink dots are your y values, and then the blue dots are x values.
No. These are look at these as being ordered pairs instead of like x or y values. This is the point 0, 0. This is the point pi 0. This is the point 2 pi 0. This is the point pi over 2, 1. This is the point 3 pi over 2, -1. Does that make a little more sense?
Yeah, that helps. Thank you.
Okay. What I'm trying to get you to, I guess, just wrap your head around for right now is that to graph a sine function, we need 5 points. And we need to know that 3 of those points are x-intercepts, and the other 2 points are the peak and valley. All right, that's the big thing, I guess, to take away from this right now. Let's look at cosine. All right, so to do cosine, we're going to have to kind of start over. I'm not going to go in as much detail with cosine, but the idea here is the same. Okay, we'd say, all right, what about cosine of x? So we write it cosine x, and then we can make a table, right? And I could start calling on people, and we could go around and do the same thing, couldn't we? But cosine is going to give us the x coordinate off the unit circle, isn't it? It's not the y coordinate, it's the x coordinate. Now, I'm not going to go through and make this table right now. Instead, what I'm going to do is I'm going to show you that picture. Now, this is cosine. Now, let's just kind of walk through this. All right, at 0, what is the x coordinate? If you plug 0 into cosine, the x coordinate is 1. Do you all agree with that?
Yes, sir.
And we're talking about the x coordinate. So we're actually measuring this distance here to here. So when I plug 0 in, right, when you plug 0 into cosine, it spits out 1. And that's this point right here. I plug in 0, it spits out 1. So this is the point 0, 1. Now, let's go to the next common angle, which is pi over 6, right there. So cosine of pi over 6, if you go look at your little first quadrant, cosine is the x-coordinate, right? The x-coordinate, and the x-coordinate at pi over 6 should be, anyone?
√3/2.
√3/2. Now, if you convert that to a decimal, it's 0.866, and the computer's rounded it to 0.9. But we're talking about this value right here. This is 0.866. And so if I go to pi over 6, which is right here, and I go up 0.866, there's my dot. Now, what's going to happen? Just think about what happens as I move along this circle. What's happening to the x-coordinate? Not the y-coordinate, the x-coordinate, as I move here. The x-coordinate is getting
Smaller.
smaller. So do you see as the angle gets bigger, the x value is getting smaller. We're talking about that little red section there, right here. It gets smaller until it gets to 0, right? At pi over 2, it's 0. And then as the angle gets bigger, now my x-coordinate is going to get negative, right? Because now I'm on the left side of the y-axis. I go to the bottom. Right here at pi, cosine of pi, I get -1. So now I'm down here at the bottom. And then I come back around. It's getting smaller. It's still negative. And then I get to the other side of the y-axis, and I have positive until I get back to 2 pi. Yes.
On the unit circle
Mhm.
where it says, is that the coordinate there, 1, 0? Is that just like the
Where?
number?
On the unit circle?
Circle
Oh, no,
where
it's
it's like pi over 2?
1.0.
Okay.
It's 1.0. You can't see the decimal.
Okay.
All right. So what do y'all think? This is cosine. After we get to this point, it's going to repeat itself, isn't it? Just keep on doing the same thing. So we are looking now at one period of cosine. This is one period of cosine. And notice that it happens between 0 and 2 pi again, right? Between 0 and 2 pi. Now I'm going to bring up a different graph to look at. That'll be very similar to this one. So here, y'all ready to see the cosine function? Here it comes. Here's cosine. I'm going to leave the sine one there for now. So the red one is sine. Where's my label? The red one is sine. The blue one is cosine. And they're very similar, aren't they? I mean, they have very, very similar shapes, but they're not like right on top of each other. It looks like we would have to move one, like maybe slide it to the left or right, and they would land right on top of one another. Do y'all agree with that? Looks like that would be true. It's actually a property, and we'll do that later. But so let me take the sine out of here so we can focus just on the cosine. So when we're looking at the cosine, let's look at what's happening. We start here, right? That's the beginning. And then it ends here, and that's happening at 2 pi and at 0, right? So we have a full period happens between 0 and 2 pi. We have a halfway point here at pi. That's our lowest point. And then we have 2 x-intercepts this time. Y'all see we have 2 x-intercepts? And then we have 2 high points and a low point. That is different than the sine, right? Show you sine again. Okay. With the sine curve, we had a peak and a valley in 3 x-intercepts. With cosine, we have 2 peaks, 1 valley, and 2 x-intercepts. But it's still 5 points, right? Still 5 important points. So for both sine and cosine, there are 5 points that if we knew them, we would be able to get the general shape of the graph. Okay. Any questions? Right. No? All right, so let's do something. I would like for us right now to just sketch f of x equals sine x. So I'm only doing this because I want you to just see how I'm going to think through this. All right. So here's what I'm going to do. I'm going to say, all right, I'm going to sketch the sine function. Here's what I know about the sine function. I know that the period is 2 pi. So I'm going to draw here. I'm going to start at 0. I'm going to go to 2 pi here. I know that there are 5 important points, and they come from cutting this in half, right? Half of 2 pi is pi. I know that halfway between here and here is pi over 2. And I know that halfway between here and here, what's halfway between here and here?
3 pi over 2.
3 pi over 2. Now you know that because of you're comfortable with the unit circle, right? You can, but I want to and that's perfect. But I'd like to show you a slightly different way to find the number between two numbers. Okay, so this is going to be helpful in a second, or like in a couple of minutes. If I want to know what number is in between these two, what I do is I take the average of these two numbers. Now, do y'all remember how to do an average? Right? If you're going to do your average of, like, let's say your test scores, you add them up and you divide by how many you have. So I'm going to take the average of pi and 2 pi. So I'm going to take pi, I'm going to add to it 2 pi, and I'm going to divide by, well, how many numbers did I have? I had 2 numbers, right? I divide by 2. So what do I get there? 3 pi's over 2, which is the same thing that Cameron said. But trust me, you'll be happy to use this in a little while. Right. So if you ever want to find a number in between two numbers, you can always just take the average of the two numbers. James?
And then does the denominator always have to be 2, or are we just doing that?
Yeah, no, if it's 2 numbers and you're trying to find the number between them, it'll always be 2.
Okay, so
I'll give you another example here. Look, if I wanted to know, let's say this number 5, and let's say the number 8. What's the number right in between? Well, real quick, 5 plus 8 over 2. Okay, 5 plus 8, that's what? 13 over 2. So that's 6.5. And you can check. If I go from here to here is 1.5. So if I add 1.5 to this, I would get 8. All right. You can always find the number between two numbers doing that. All right, so going back to this, I said it's a sine function. I know the period is 2 pi. There's 5 important points that I'm going to need. And so I put the halfway point, right? I put the halfway point, and then I put the halfway point in between those 2 points right there. So between the beginning and the halfway, I did half. And between half and the end, I did half. Now, here's where I have to know what the sine function does. I have to remember that the sine function starts at 0, ends at 0, and has a 0 in the middle. I have to know that. I also have to know that at this midway point between these two, that's where I'm at my peak. And I have to know that at 3 pi over 2, this is where I'm at my valley. And then once I have that, I can connect the dots together and have a general sketch. All right? That's how I'd sketch sine. Cosine would be the same thing. If we wanted to do cosine here instead, I'd say, okay, cosine has a period of 2 pi. So I write down 0 and 2 pi. Then I say I'm going to cut it in half. There's pi. And then I'm going to cut that in half and that in half. So I've got my 5 different locations, right? 1, 2, 3, 4, 5. Now I have to remember that cosine starts at 1 up here and ends at 1. I have to know that halfway is where it has its valley. And I have to know that at these 2 points are where the x-intercepts are. I have to remember that. And then I draw my picture. One more thing I'd like to point out about the cosine curve. I think the sine curve is easy for people to draw. Right? Most people can draw the sine curve because when you do the sine curve, once you have these points, I think most people are pretty okay with just drawing like a hill and then a valley and then they're done, right? But most people can just do that, no problem. Cosine's a little weird, so I want to just kind of point something out to you. It's not weird, it's just people can mess it up. So let me show you what I mean. When you're drawing cosine, you have your points here, right? I want you to just focus your attention on this first part. This first part is not like this. It's not a straight line, right? What it is, I like to look at this as being almost like, oops, forgot to put the pin. Oh, shoot, I don't know what I just did there. I like to look at this section right here as being like the side of a frown. You know, like if you have a happy face or you have like a sad face, right? This part right here looks like this side of the frown. And actually in Cal 2, I'm sorry, Cal 2, in Cal 1, we study this. This is called the concavity of the function. And we would determine in Cal 1 that this function is concave down here. But that's not important. It's just, I don't want you to draw something incorrectly. So it must look, this section right here must look like the right side of a frown. With me? Then this section from here to here must look like the what? What do you think? In
The
terms
left
of
side of the happy face.
the left side of the happy face. It must look like this side right here. So we've got the right side of a frown followed by the left side of a happy face, and then right side of a happy face, and then left side of a frown. Okay, so you should be drawing little frowns and smiles, no straight lines. You know, it doesn't look like, it's not like a jagged, like, you know, down, up like that. It's curved, right? Okay. I think it's time to get down to the more important business now. We've got the basic idea of what a sine and cosine
That's
look.
the cosine graph, correct?
That's the cosine. Yep. Yeah. If you want to look at sine, we could do the same thing for sine. It's just students seem to do better with sine. I don't know why. For sine, it's just what? Frown turns into smile, right? Frown goes to smile, and that's it. You're done. Here's kind of like where it transitions. You got your frown and then you got your smile. In Cal 1, we actually have a name for where it changes from a frown to a smile. We call that an inflection point, but we're getting ahead of ourselves. All right, back to business. Let's take a look at another graph. I want us to sketch f of x equals 3 sine x. So there's something different here now, right? It's not just sine x, it's 3 times sine x. So can somebody tell me, like in words, what they think this 3 is going to do to this graph?
Maybe like multiply everything by 3, kind of.
Yeah, so what do you think that would do to the graph?
It would expand it.
It's gonna
Like-
expand the domain, isn't it?
Yeah, because wouldn't you start at 3, 0 or 0, 3?
Well, okay, let's go back and look at the graph of sine. Here's the graph of sine, right? Let's just start at this first point. This, now remember, this is sine we're looking at, right? So that's the point 0, 0, right? And then let's go to this point. This is the point pi over 2, 1. Now this is the function f of x equals sine x, right? I'm asking us to look at the function 3 sine x instead. So if I plug in 0 into this, sine of 0 is still 0, isn't it? But then I multiply that times 3, and 3 times 0 would still be 0, right? So that point is still there. 0, 0 is still here. Let's see what happens here though. What if I plug in pi over 2? What is sine of pi over 2? Now hold on, don't answer that. Angelique? No, I called on you last time. Allison?
I'm here.
Hey, Allison, what's sine of pi over 2?
Sine of pi over 2 is it 0, 1 or 1, 0?
Well, it should only be a single number. Sine of
Oh.
pi over 2. What's
Is
that?
it 1?
It's 1. Okay. So if we plug pi over 2 into this one, sine of pi over 2 would give us 1. But then what do we have to do with that answer?
You
Times
have
it.
to divide it.
Multiply it by
Multiply
3,
it.
right?
Okay,
So 3 times 1 would be 3.
3.
So for our graph, we have the point when we plug in oops, I messed up. We have for our graph, this one, that when we plug in pi over 2, it doesn't spit out 1, it spits out 3, doesn't it?
Yeah.
So our graph should be further up. Actually, I can't put it here because it's off the graph, but it should be up here, right? Our point should be here. So let me clear all this crap out of here. We know that that point's there and then that point's there. And if we keep doing this, what we're going to find is that all this does is stretches the graph out vertically. Now I have a much better way of showing this to you. Okay, let me clear this out. Bring this back in here. Okay, so you ready? Here's the graph of sine. Let me move it over. Okay, there it is. Now watch what happens. I have this set up so that I can adjust the number in front of sine. So the number in front of sine here is this A1, and right now the value of it is 1, but I'm going to change it to 3. So watch. See that? All it did was stretch the whole graph out. Did it change our x-intercepts? Did it change our x-intercepts?
Just the range changed to 3, -3.
Just the range. Yeah, you know what I'm going to do here? I'm going to graph just sine x below it, or just next to it.
Sir, I have a question.
Yep.
Just to clarify, if we were to do the input-output thing with the x and y, it's just we multiply our y's by 3.
That's right. It's all we're doing is multiplying all of our y values by 3. That's all we're doing.
So would that make the 3 pi over 2 -3, right?
It would be -3, exactly. Yeah. So look down here, see we're at -3.
Okay, yeah.
So what I've graphed here for you, the dotted one is the original sine function. Okay, that's what sine of x looks like. The red one is 3 sine of x. And so do you see that everything got stretched out? Everything got pulled. All the points got pulled up. But notice it did nothing about the x-intercepts. Why don't the x-intercepts get pulled? Well, because the y value is 0, right? So if we multiply 0 by 3, it's still 0. So nothing changes in terms of the intercepts. The only thing that happens is our peak got higher and the valley got lower, and all the points in between got pulled.
I have a question.
Yep.
Is this rule the same for the graph of cosine as well, or is it just
Oh,
for
yeah.
sine?
Nope, it's for cosine as well. Yep. So let me just show you right now the number in front. We're looking right now at the red one is f of x equals 3 sine of x. And what I'm about to do is I'm about to change that number 3 and just watch what happens to the graph. I'm going to make 3 bigger. So if I make 3 bigger, it stretches it out further. If I make 3 smaller, look, I can even make the number in front a fraction, like 0.4. And look what's happening to it, right? It's getting smaller. Now, it wouldn't make sense to put 0 there, because if I put a 0 here, it just kills the whole function off. But check out what happens if I put a negative number. So let me go back. Here's positive. Here's 1 in front. Here's a fraction in front. And if I go negative, boom, it flips it over. Do you see that? It reflects it. It reflects it. And that happened in college algebra too. When we put a negative in front of a function, it flipped everything over the x-axis. Exactly the same here. So we have a special name for that number that's in front of our sine function because it changes how high and low, it changes the range of our function. We call it the amplitude of the function. So in general, no, let me sketch this, okay? Let me do this and then I'll get back to the definition. So if I were to sketch this, here's what I do. Boom, boom, and I want you to notice how fast I'm doing this. I know it's a sine function. I know that that's 3, that's going to stretch everything out. So I know it ends here at 2 pi, halfway is pi. My quarter marks are pi over 2 and 3 pi over 2. I know that because I know that now. I'm a pre-cal student and I should know that by now, right? Those are the major points. Okay, I know that for sine, I start here, I end here, halfway in between, I've got an x-intercept. So those are all my x-intercepts. Those don't change. And now what changes is that my highest value and my lowest value, those change. So this is no longer 1, it's now 3. And this one down here is -3. And if I draw this like this, I'm done. Okay, so it looks exactly like the sine. I just put 3 here, -3, and that way everyone knows it's been stretched out. Any questions?
So with putting a number in front, so if it was a -3, it would still be the same. We would just start negative, correct?
Yeah, let me do that one. So let's say we wanted to do this. Here's what I would do. I say, okay, this is a sine function. And I would say, all right, right here tells me that everything got stretched, everything is being stretched out by 3, right? So my peaks and valleys are going to be at 3 and -3 instead of 1 and -1. However, the negative in front is going to flip that whole answer over. So how would that impact things? Well, I still go 2 pi, I still go pi, I still go pi over 2, I still go 3 pi over 2. Okay, and now I have my x-intercepts. I know that they start here, end here, halfway. Now, originally, if this did not have a negative in front, I would put the 3 here and the -3 here, and I'd be done. But because there's a negative, I need to flip those. So I'm actually going to put this point down here at -3, and this one gets flipped up to +3. And now when I connect them, oh, yeah, good enough. There it is. See that? That point came down and that point came up. Everything got rotated.
I have a question.
Mhm.
So if we have the amplitude in front of a cosine function, would it still be considered a vertical stretch? Or because we're working like with the x-axis there, would it be a horizontal?
It'd still be a vertical stretch. Yeah,
Okay.
let's do a cosine. Yeah, I think we're ready for a cosine at this point. So let's start off with the basic one. Okay, if I were to, do I need to do cosine by itself, or can I go to like 3 cosine? You all ready for 3 cosine?
Yes, sir.
Yeah.
Yes.
Okay. So 3 cosine x. So I look at that and I go, okay, I know it's a cosine function. I know there's a 3 in front that's going to stretch everything out by 3. Now things are going to be a little different here. All right. So pay attention to what I'm going to do. I know that it has a period of 2 pi. I go halfway, halfway, halfway between those. Okay, now the points. This is the part that's different. I'm going to do in orange, I'm going to do what the normal cosine would be. I have an x-intercept, x-intercept. I would have up here, well, I don't want to go that high. Up here at 1, I would have a point here. And at -1, I would have a point like halfway. At the halfway point is where I'm at the low point. And at the end, I'm up here at 1. So this is what the original cosine would be, right? Frown, smile, frown. That's what cosine looks like. But everything has been stretched by 3. Does that have any impact on the x-intercepts? Stretching by 3.
No, they'll stay the
No.
same.
They'll stay the same. But everything that was 1 or -1 gets hit by a 3. So that 1 that's here actually moves up to 3 now, doesn't it? And that means the 1 that was on the end also goes up to 3. Right? So this point got hit by 3. This point got hit by 3, so it came up. And then this one that used to be -1 is now -3. So it comes down like that. And now we have to still do this. Frown, smile, smile, frown. Questions? No? While we're here, what if we did -3 cosine x?
It would just flip it.
It would just flip it, right? So the x-intercepts would not change. These would stay the same. But everything that was positive now becomes negative. So that point's going to come down here to -3. That point up here is going to come down to -3. And this point that was here is going to come up to +3. Now you have to be a little careful here with the way you draw this, because remember, you got to use smiles and frowns here. This is going to be smile, frown, smile. Can you all see that that's just a reflection over the x-axis? That's all that is. How are y'all doing?
Good.
Good. Anyone have any questions? Because we're about to move into the part that's the hard part. This is the amplitude is the easy part. The next part's the hard part. No? Okay, let me define real quick. If you have amplitude, okay, amplitude. So basically, if you have f of x equals, the book uses capital A in front of sine of x, or if you have some function with capital A in front of cosine x, then A, the absolute value of A, sorry, is called the amplitude. Now just, so if you look at both of these, right? The amplitude of this one is 3. The amplitude of this one is also 3. So they both have the same amplitude. The thing that's different about them is that one of them is a reflection, the other one is not, all right? But they both have the same amplitude. All right, so let's do this. Y'all sure? Y'all are ready to move on? Okay, let's take a look at this. I want us to try and sketch this. So sketch. I'm going to let you think about that for a moment. And go refill my drink. I want to just see if you can maybe mess with that a little bit. Don't just get your graphing calculator. I want you to think about what that might do, because I've put a 3 here, but it's not a 3 in front. The 3 in front stretches everything out vertically. What do you think this does? Now, again, don't answer. Just think about it for a moment. I'll be right back. Okay, did anyone have any guesses as to what that would do?
Is it going to
Horizontally stretch it?
Oh, hold on, I've got a couple of people. Cameron, I saw you unmute first. Oh, yeah, go ahead, Cameron.
Well, I was gonna say, since it's in the parentheses, it would be affecting the x values. So I'm thinking maybe it would shrink it.
Okay, shrink it. Yeah. Which way do you mean shrink it? Like the amplitude shrinks?
I would say maybe, I don't like, maybe since it's the x values, maybe they'll come in.
Okay, so you're thinking it might have an impact on the period then?
Yes.
Because your standard sine and cosine does a full period between 0 and 2 pi. And you're saying that maybe the 3 changes that period, right?
Yes.
Yeah, that's a very good analysis of that. Let's see. Why don't we just take a look at it? Okay, I have this all set up to do it anyway. So here we go. Let me go back to the standard sine curve where our amplitude is 1, maybe. There we go. That's our standard sine curve. And notice that here I have this W1. Okay, that's a number in front of X. Okay, so right now we have, this is 1. And the number in front right now is 1. Do y'all see that in front of this X? I'm going to change it to 3. Ready? Watch the graph. Okay, do y'all see what happened? Do it again. See? Let me go even further than 3. I'll go out to 10. So Cameron, you're correct. It's having an impact on the period. See, notice the amplitude is not changing, right? The amplitude is staying the same. It's just, what's another word for that? It's happening, we're having these squiggly,
Frequency?
up and downs. They're happening more.
So it's like compressing the graph?
It's, in this case, it's compressing, right? So we're having
It changes the frequency.
Frequency, right? These little curves, these little periods are happening more frequently. And actually, this has to do with waves, okay, like radio waves, microwaves, gamma rays. All of electromagnetic radiation has amplitude and frequency, right? Like, you probably don't know this, or maybe you do, but when you turn on your radio, I don't know if anyone still listens to the radio in the car or not, but like when you turn into like you turn into some station, I don't even know what stations people listen to, but if, let's say, you tune into 97.3, right? You are changing, you're making your receiver listen for a certain frequency, okay? So it's looking for certain waves that have a certain frequency to them, and that's where you're getting the music from. And when you change your station, what you're looking for is different frequencies like this, right? So one station is broadcast with a certain frequency, and another one's broadcast with a different frequency. And that's why when you are if you have 2 stations that are really close to one another on the tuner, then you can like sometimes hear the other one. It like crosses in. And that's because the frequencies are so close to one another. And you probably, I don't know, does anyone know what FM and AM stand for? FM, you know what I'm talking about, right? FM versus AM on your radio. Y'all do listen to the radio, right? Y'all know what I'm talking about, right? Yeah. I mean, okay, so FM stands for frequency modulation. So what you're doing is you're tuning into different frequencies. Any idea what AM would stand for?
Would that be amplitude modulation? Amplitude
modulation. So there you're looking for waves where you're looking for differences in the amplitude, not in the frequency. Anyway, okay, we're getting off topic. All right, so look, amplitude and frequency. Amplitude, we're done with for now. Somehow the number in front, let me go back to 3. The number in front had an impact on the period. So let me bring the original sine function in here. There's the original one. So I'm going to point out here on the original one, where our important points were. Here, 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 right? here, and here. So that on the original sine function, there was our period, right? On sine of x, the period was 2 pi. Okay, let's look at the new one. This 3x inside the sine. Check it out. It goes up, it goes down, goes back up, right there. We have a period here. This is sine of 3x. And so the period of this one, I actually can't tell. It looks like it's somewhere around here. Do y'all see that? We have changed the period. I honestly can't tell you right now what it is. All right. But that would be something we would need to know, right? If we wanted to draw this, we would need to know that period. Do y'all agree with that? Okay, so here, let's go and do this. So the main thing to take away right now is that if you change the number in front of the sine, it changes your amplitude. If you change the number inside next to the x, it changes your frequency, okay? It changes your period. So luckily for us, we have a formula. All right, here we go.
What would happen if the number inside the parentheses was less than 1? Would it make the frequency longer so it was less frequent?
You mean, let me show you. Okay, so you're asking what if that number in there, here's 1, right? Here's 1. So let me do something like 0.5. Oh yeah, look at that. What did that do?
What if you do a negative?
Yeah, I'll do a negative. But so what did that do? Maddie, you were asking, right?
Yeah, it widens it.
It widened it, right? It widened. So it still changed your period, right? But it made it really a long period instead of condensing it. So it looks like if that number in front is 1, it's just the regular sine function. If it's bigger than 1, we get more, it's more frequent. If we go between 1 and 0, it becomes less frequent. So longer wavelengths is what it's technically called. And now you ask, what if we go negative, right? So here goes negative. Okay, so when you go negative, it's hard to see it. So I'm going to go to -1 and zoom in. So what it did, it's hard to tell, but what it did was it took the original sine function and it reflected the whole thing over the y-axis. So if you take this sine curve right here, the dotted one, and you flip it over the, did I say x-axis? Y-axis, then it draws the red one. So that's what the negative in front did, is it's a reflection over the y. And then the further out you go, the more frequent you get. We'll talk about that. We'll get to that. Good questions. All right, we need to get back to this. So how are we going to sketch this? So right now, we kind of don't know how to do this. So I need to give you some information. Okay, if f of x equals a sine of, now the book uses this, they use the omega, okay, it's a Greek letter. I don't know why they use omega. It has to do with wavelengths and stuff, but omega x, okay, that's the letter that they use. So for us, this is 3, right? Omega is 3 for us in this example. So if you have a function where you have a in front of sine and then you have omega x, the period of this will always be equal to 2 pi divided by omega. And that's what you need to know. Okay, 2 pi over omega. Now think about it. If we have the original sine function, just the original basic sine function, sine x, what is the number in front of x? We don't
1.
write it. It's a 1, right? That's a 1 there. So if I put it, that means omega is 1. If omega is 1, what's the period?
2 pi.
Pi, right? So it matches up with what we already kind of knew, right? But now this works for any number in front. All right. All right, so let's get back to this problem. I still want to try and sketch this. So here's what I know. I know omega is 3. And that means the period is 2 pi over that 3. All right, you ready? This is where things get weird. This is where things get weird. I'm ready to start to try and draw this. Now, I know for all sine functions, I have 5 important points. 3 of them are x-intercepts. The other 2 is the peak and the valley, right? That's what I know. I need to know where those 5 important points are. And here's the only thing I know at this point, is that it starts at 0 and it ends at 2 pi over 3. I know that because I just calculated what the period is using a formula that was given to me. Now, before, this was easy because it was 0 and it was 2 pi, and then we just went halfway, didn't we? But now we actually have to figure out what that is. So what is halfway between these two numbers?
We could just take the average.
We just take their average, right? That's all we do. So I'm going to do that over here on the side. To figure out what this is halfway, I'm going to take 0. I'm going to add 2 pi over 3 to it, and I'm going to divide by 2, which is 2 pi over 3 over 2. Now, students always seem to have trouble with this. When I say students always have trouble, I don't mean always. You know what I'm just kind of making the point that I know students struggle with this sort of thing. You have a fraction over 2, right? So I look at this as a fraction over a fraction, and that means 2 pi over 3 times the reciprocal of 2, which is 1/2. So in other words, I'm turning division into multiplication. That's what I'm doing. And now once I do this, the 2's can cancel, and I multiply straight across, I get pi over 3. So that is pi over 3. Now I have to figure out what this one is. So I need the average between 0 and pi over 3. So let me do that over here. 0 plus pi over 3 over 2. This gives you pi over 3 over 2, which is the same thing. You do 2 over 1. So this is pi over 3 times 1 over 2. And when you multiply straight across, you get pi over 6. So this is pi over 6. And I also need, let's see, I have blue here. I need that number, which is halfway between there and there. So let's just make sure I'm doing a little check here, make sure people are paying attention. Genesis?
Yes.
So what am I going to do? Tell me what I'm about to do. I'm looking for this.
I'm gonna add 0. I'm not really sure.
Okay. Yamna? Yamna, no? Jackson?
Hello. You would add pi over 3 and 2 pi over 3.
Okay.
Be
Yep.
pi over 3.
So pi over 3, I'm going to add that to 2 pi over 3 and then divide that by 2, right?
Yeah.
So Jackson, what you're doing is you're trying to find the number between these two numbers, so you take the average of these two numbers, right?
Yeah.
Okay, so that's kind of a big takeaway today, right? Like most of you coming into this class probably didn't know that that's what you do to find the number between two numbers. I know that, again, from experience. I know a lot of students don't know that, but it's a very useful thing. Okay, so we add these up, and you said this was what?
Well, it could be 3 pi over 3, but then you can cancel out the 3's, so then it's just pi over 2.
Yep, pi over 2. Okay, so when you add those together, you get 3 pi over 3, get rid of the 3's, and now you just have a pi and then divide by 2. So that's pi over 2. Good. All right, there we go. Okay, the hard part's over. The hard part's over. Now we know what a sine curve looks like. It starts at 0, ends at 0, and in the middle at 0. Our amplitude here was 1, right? There was a 1 in front here, so there's no flipping of anything, and we know it goes, the highest point's 1 and the lowest is -1. So I'm just going to put a 1 here, put a -1 here, and now just connect, frown, smile. Now remember, in reality, this continues, right? It keeps going in both directions forever, but I'm only going to be asking you to graph one of the periods. All right, we have about 8 minutes left. Let's do another one.
Professor, I have a question.
Yep.
When would we flip for, so like whenever we're doing to find like the middle point, would there ever be a time when we flip the x? So like how we're flipping the y, flipping the reciprocal, would we ever do that for the x or no?
I'm not quite sure I understand your question.
So just like on the example, we'll do the last one where we did pi divided by 3 plus 2 pi over 3. And would there ever be a time where we would flip it and we would do 3 over pi or no?
I'm still not quite following it. These two go together to become 3 pi over 3, right? And then the 3's cancel, and I just get pi. You're asking if there's ever a time that we'd flip, and I guess I'm just not following where you would want to flip here.
Or not necessarily this one, but like the previous ones, how we flipped the 2 over 1 to 1 half. Would we ever flip the 3 over pi like that or no?
No, because what we're doing is we're saying this. This goes back to, I don't know what class, but if you take a fraction and you divide it by another fraction, that's the same as taking the original fraction and dividing it by the other fraction, which is the same as taking that fraction and multiplying by the reciprocal. So you're always going to be flipping the bottom one, never the numerator. This one never flips. It's always the denominator one that flips.
Okay, yeah, I get it now.
Okay. All right, so let's do this one. Let's go -1/4 cosine of 3 pi x. Okay, here we go. So we look at this. I only have about 6 minutes left. So we look at this and we know it's a cosine function, right? The amplitude of this, what's the amplitude?
1/4.
Okay, the amplitude of this is going to be the absolute value of this, which is 1/4. I'm also going to remember that this thing is going to be flipped over the x-axis. How do I know that?
Because there's a negative in front.
There's a negative right there, so I know I'm going to have to flip my answer. And then what about the period? The formula is 2 pi divided by omega, or W. What's omega for us? What's W for us?
3.
3 pi, right?
3 pi. So it's the whole thing. That's omega. It's everything in front of x.
And then would the pi's cancel out?
In this case, the pi's would cancel out. And you get 2/3. Okay. So let's now try and graph this. So I've got my axes. I know that this is a cosine, right? This is cosine. So I need to get these 5 important places. I know that I start at 0, but in this case, I don't end at 2 pi. I end at 2/3, right? Because that's the period, 2/3.
I have a quick question.
Uh-huh.
So since the negative's on the outside, like you said, you flip it over the x-axis.
Yep.
If the negative's on the inside, would you flip it over the y-axis?
Yes, but
Okay.
yes, but we're not there yet.
Okay.
We will do that, just not yet.
Okay, thank you.
Uh-huh. All right, so now I need to get halfway between, right? So I need to get this halfway point. So I add those two numbers together. That's just 2/3, and I divide that by 2, right? That's what I'm doing. 0, 0 plus 2/3 is just 2/3 divided by. So this is 2/3 times, I'm going to rewrite 2 as 2/1, so times a half. And the 2's cancel and you just get a third. So this is a third. Here, we're going to go 0 plus a third. I'll do it on the side here. Over 2, that's a third. Over 2/1, which is a third, times 1/2. So flipping again, you get 1/6. And I think the hardest one is this one right here, because you have to do a third. Oh, maybe not. Plus 2/3 over 2. So that's 3/3 over 2, but that's just 1/2 because 3/3 is 1. So 1/2. Any questions? I have 2 minutes.
And then to graph it, we would just start below at -1/4 and start.
Yeah, this is going to be kind of up to you how you want to do this. The way I do it is I put what my amplitude is. So I know this is 1/4, and I know this is -1/4, right? So I know that's like the highest and lowest points. Then I always like to put the x-intercepts first. I know that for a cosine, my x-intercepts happen at the 1st quarter and 3/4 mark. Those are the x-intercepts. And normally, a cosine function would look like this, normally. But because I'm flipping it, I need to put this point here, the one that would have been here goes to the bottom. The one that would have been on the bottom is going to go to the top. And the one that would have been on the top here is going to go to the bottom. And then I'm going to draw a little bit of a smile, frown, frown, smile. There we go. All right. So let's check our answer. I'm just going to go to a blank graph. I'm going to go -1/4 sine of 3 times pi times x. Okay, there it is. And where were it was 2/3, right? So let me see if I can't do, it doesn't do fractions, does it? Okay, but I think we can see it from here. I'm only going to go from 0 to, what was our period? 2/3, right?
Yes.
Okay. Oh, shoot, that didn't work. Why didn't that work? 0?
Because you're still in sine, you're not in cosine, I don't think.
Oh, I need to put cosine in. Yeah, sorry. That would be a mistake. Okay, I don't know why it's doing that, but it's okay. Oh, I know what to do. I know what to do. Never mind. Cosine. There we go. I have to do it here. And I say 0 less than or equal to x less than or equal to 2/3. There we go. That's what I did. Forgot it. Forgot how to do that here. Okay, so there it is. So this is 2/3. That's 0.6666 forever. This is 1/3. This is a half. This is a sixth. You can see at -0.25. Go up, over. So it matches what we had, right? Okay, that's it for class. I have not done the homework for this section. I will get on that either later today or tomorrow. And you know, this is the end of what will be on the test. All right. Okay. Well, thank you, everyone. And, you know, for those of
I
you
have
who
a
need to go
question.
get on pace, you know, go get studying, go back, review your notes and everything. What's the question?
On the exam, will there be word problems?
Anything that was on the homework or anything that we've done in class is fair game.
Okay.
I do intend on giving you some sort of review for it, some sort of guidance, but right now at this point, what I would do is focus mainly on reviewing your homework and then just going through the problems that we did in class. You know, look at what you've written down, lecture notes, the types of things that we discussed. I won't deviate from that. All right. I haven't made the test and I haven't made the review. So once I make the review, you'll have a much better idea of what to focus on.
Thank
I have
you.
a question.
Yep. You can leave if you need to go. Yes.
Thank you.
I have a question.
Yes.